In the first video, we set up the drive with these parameters and we learned about our system. In this video, we'll set up PID using the trial and error method. Parameter 7.0 enables PID. We know from the last video that we have a forward-acting system. And let's make PID active in either remote or local modes so we don't have to worry about which mode we're in while we're testing. Parameter 7.02 is a read-only parameter that tells us where the PID set point is coming from. This is telling us the drive will use the keypad entry for set point, which is what we want, so no changes are required. Now, where would we change that if we want the set point to come from a remote PLC, for example? Well, in parameters 4.0 and 4.1, just like we do for normal drive operations. That's where we always set up our analog input source. It doesn't matter what mode we're in. Now that PID is enabled, forward acting is specified, and the set point source is set up, we can finally set up PID. To do that, go to parameter 725 and set it to a 1. That selects this PID mode, the independent or parallel PID mode. We'll explain the difference between these two diagrams in the loose ends video. I love this chart because it shows me everything I need to know about PID at a glance. This is the set point stuff we just did. This is supposed to look like a switch. When PID is off, the set point is the drive frequency in hertz and it goes straight out to the motor. When PID is enabled, it takes the feedback from the sensor via whichever source we select, compares it to the set point number we told the drive to try and maintain, that would be the 6 psi number we used in the previous video, and uses the difference, or error, to create the frequency that goes out. It's really important to understand that when PID is enabled, the set point we enter, and is shown on the LCD, is now a percentage number, so we can subtract it from the sensor reading, or process variable, which is also in percent. We enter the set point via the keypad, where you would normally put the drive frequency. But again, we have to remember, this is a set point percentage number now, not a drive frequency. We want our system to maintain 6 psi, which is 40% of the sensor's full scale. So here, where the drive frequency would normally be, we need to put 40%. But this is still entered in hertz, so we enter 40% of the drive's max frequency of 60 hertz, which is 24 hertz. I know that's confusing. Just remember this isn't the drive frequency when we do PID. It represents 40% of the drive's full-scale output. And look at this. You can always check that you got it right by looking at parameter 705. It shows you the current set point in percent. Yep, 40%. Perfect. Remember, while our set point is coming from the keypad, you can have it come from an analog input or even a remote PLC. So this is a great way to verify the set point is what you think it should be. If we set parameter 8.0 to a 10, we can monitor the feedback signal right on the LCD display. That's almost the same thing as the analog input we were monitoring in the first video, but this shows us the feedback signal we selected for use with PID, which is great because we know analog input 1 is working from the first video, so if we don't see it working here, we immediately know we selected the wrong function for analog input 1 in parameter 4.02. Yep, analog 1 is definitely the source of our feedback signal, which we also call the process variable. Well, great. We've enabled PID, set up the set point, selected the PID mode, and we verified that we set up the feedback signal correctly back in the first video. We can finally tune the PID loop. That's this stuff. And for this video, we don't need any of this. We'll cover all that stuff in the loose ends video. We know from the last video, our system needs to run around this frequency range, so why not just tell the drive to go hang out there and then just have PID make minor corrections around that as the load changes? Well, that's exactly what this is for. It selects where the offset's coming from. We want a fixed offset to generate that 6 psi, which comes from parameter 704. You can also have a dynamic offset via an analog input. Again, this is a percent value, not hertz. Everything we do in PID is in percent. We know from the first video that the drive needs to be around 31.2 hertz to get the system to 6 psi with one valve open. Well, that's 52% of the drive's 60 hertz. So even if all of this is 0, the drive is still going to run at this offset frequency of 52% of the 60 hertz, which is 31.2 hertz. And now all this PID stuff has to do is just make minor corrections around that offset, which will require smaller gains, which means it'll be easier to set up a stable PID system. Let's try it. Let's go to parameter 713 to set P to 0, parameter 714 to set I to 0, and parameter 715 to make sure D is 0. So now only the offset should affect the drive's output. I'm going to bring up the GSoft 2 application, connect to the drive, and open up the scope function so we can watch all of this graphically. We'll make green the set point we want the drive to maintain in percent. That's this guy. Yellow, the sensor feedback, also in percent. That's this guy. Red is the difference between the two, this error signal. And we'll make light blue be the actual frequency command being sent out, this guy. If we start the scope and run the drive, and then open each valve, and then close each valve, and pause the scope, and zoom in on that, we can see that these boxes show the values at the current cursor location. Sure enough, the set point is at 40%. The feedback from the pressure sensor settles at about 40% with one valve open, and changes as we open more valves. The drive frequency is fixed at the 31 Hz offset we entered as 51.8% of full scale. And the error is the difference between the green and the yellow, and it settles out around 0 for one valve and increases for each additional valve. Perfect. Exactly what we expect. So this scope trace is just a graphical view of what we did in the first video, right? As we open each valve, the system pressure drops. Well, let's turn on the PID parameters and see what happens. We'll leave I and D 0 and just work on P first. How is P used? We take where we want to be, the set point, and subtract the feedback signal that tells us where we actually are to get the difference, or error, between the two. Multiply it by P and add it to the offset. The bigger the difference, the more we change the offset. So we're modifying the offset by an amount that's proportional to the difference between where we want to be and where we actually are. That makes sense. So P is just a proportionality constant, or you can think of it as a gain value that determines how much this difference affects the drive frequency. So how do we figure out how big P should be? Well, we know from the first video that on average, the pressure drop between valve openings was about 4.2% on average. And at the corresponding frequency increase we needed to overcome that was about 4.4% on average. So, what do we need to multiply this pressure drop by to get this increase in speed? Well, it's 1.05. That's P. It just scales this difference to give us the additional frequency we need to maintain the pressure. Let's rescale the scope display so it's easier to see the traces in the next test we run. Let's go to parameter 713 and enter the 1.1 as our starting point for P. I and D are still 0. Hit enter and, what happened? The drive went berserk and shut itself down. All we did was add a little more frequency output, right? It's like the drive's trying too hard to compensate. Did we have too much gain? Was P too big? Let's cut it in half and try again. Well, startup looks a little messy. Let's open and close the valves. I'm still getting a lot of messy oscillation. So what's going on here? Well, the issue is noise in the feedback signal. If we set P back to 0 and rerun the open loop test and zoom in, look how big the noise is compared to the pressure drop we're trying to measure. We told the drive to compensate based on this difference, but the noise from the sensor is adding and subtracting this much to that at random. So the drive is going nuts trying to keep up. We'll take a closer look at why the pressure signal is so noisy in the system and what we can do about it in the loose ends video. But for now, assume we're stuck with this noisy signal and we just have to deal with it. The good news is the GS4 has an easy fix for this. We simply go to parameter 413 and add some filtering to analog input 1. If I zoom way in on the noise signal, we see some fast-moving noise and a slower undulation that's around a couple tenths of a second. So let's set the filter time to something just a little bit longer than that. How about a quarter second? Now before I hit enter, let's get the scope running so we can see the unfiltered noise. Then I'll hit enter. Wow, what a difference! And in the big picture, the noise is almost gone. Much better. We could tweak the filtering value even more, but for now this is fine. We'll cover the filtering do's and don'ts in the loose ends video. Okay, the analog signal looks a lot better now, put P back to our original 1.1. Let's open the valves and close the valves. Now that's more like it. And look, we can now see the drive is automatically adjusting the frequency to try and compensate for the pressure drop. Looks like we have nearly a 5% error between the set point and the feedback signal. So it's time to get more aggressive with P. I like to double P until things go haywire. And open the valves and close the valves. Looking better. We're down to a 3% error. Let's double P again. Uh-oh, the system's starting to oscillate. That means P's too big and the drive's trying too hard to compensate. Let's split the difference. How about 3.0? Great, the oscillation stopped. That's good. Open the valves, close the valves. That looks pretty good. We got a little overshoot and then it settles out pretty quickly. And the error is down to a little over 2%. I ran one more test with P set at 3.5, and as you can see, the oscillations were starting up again. So we'll stick with P set at 3.0. As you can see, we could play with this all day just to get a value of P that we're comfortable with. That's why we call it the trial and error method. But P didn't quite get us there, did it? It never did get the sensor feedback value back to the set point we wanted, did it? We still have some error, and we want that error to be as close to 0 as possible. So it's time to enable I. I just sums the error values over some length of time and uses that to adjust the output frequency. Different systems use different kinds of integration equations. This drive uses an I that gets more aggressive as it gets smaller. Looking at our data, if we sum the error over this entire duration, the result will be heavily impacted by all of this stuff. I'm going to say that by the time I get here, I'd like to have a stable sum. I don't want this stuff to impact it, so maybe we'll make our duration about this long. And we'll call that 1/10 of a second. So we'll go to parameter 714 and enter that for I. If I restart the scope and run the drive, we immediately see the impact the I value has on the system. It is helping, but it's taking way too long, around 7 seconds to get the pressure back to 6 psi. That's way too slow, so let's cut the I value in half, restart the scope, open some valves. Okay, now our error gets to 0 in about 3 seconds. Cut I in half again. It settles quicker. And let's cut I in half one more time. So look at this. The drive is now automatically adjusting the frequency when the pressure changes in less than 3/4 of a second to automatically maintain the system pressure regardless of how many valves are open. That's pretty good. And we only needed P and I to do it, which will be the case most of the time. It'll be rare that you actually need D. We'll talk about the D parameter and these other blocks that we didn't use in the loose ends video. Could we continue to tweak this and make it better? Sure. It just takes time and patience, which is the big problem with this approach, right? Time. Shutting down an operation while you take the time to go through this trial and error process can be very costly. And at the end of the day, the results are still just a guesstimate that, depending on how much time and effort you put into it, may or may not be optimal or super stable. Also, with this trial and error method, you usually push your system into oscillation to gauge where you are. In our little pressure demo here, there was no harm in doing that. But many systems can't handle that kind of abuse or might even cause catastrophic failure. So, is there a way to find PID constants that doesn't take the system down for long periods of time and doesn't go into oscillation? Yep, and we'll do that in the next video. Click here to learn more about the GS4 Variable Frequency Drive. Click here to learn about Automation Direct's free support options, and click here to subscribe to Automation Direct's YouTube channel so you'll be notified when we publish new videos.